Yeah.
Uh, so if there's more intermolecular forces, substances are going to be more viscous. So what else? We discussed solubility. There's another thing. Did we talk about reactivity?
No.
Okay, so even reactivity kind of depends, sort of depends, not entirely, but reactivity also matters on intermolecular forces. For example, you have a nitrogen molecule, right? It has a triple bond. Amal, do you have any idea? Is it reactive or unreactive? I mean, this nitrogen molecule,
Yeah.
is it reactive or not?
Mm.
I mean, 78% of the Earth's atmosphere is nitrogen, but it's very inert.
Yeah.
And one of the reasons it's very inert is it isn't reactive. One of the reasons for it being very inert is that it's non-polar. I mean, it's a non-polar molecule because both atoms are nitrogen. Uh, so it doesn't really attract other molecules. Then you
Okay.
then you have another molecule which has a triple bond, like a carbon monoxide molecule. That's a very polar molecule, which means the oxygen has a slight negative charge and the carbon has a slight positive charge. So it attracts other molecules. It's a polar molecule. And since it's a polar molecule, it's kind of very reactive. Like if you know carbon monoxide.
Yeah.
Okay, so if you have carbon monoxide, that's extremely reactive. Uh, and it's very unstable as well. It quickly reacts with oxygen or any other thing and gets converted to carbon dioxide or some other substance, but nitrogen doesn't react. So if molecules don't attract other molecules, they're not going to be very reactive. If
Yeah.
molecules attract other molecules, they're going to be extremely reactive. Okay, so it kind of affects the reactivity of the substance as well. Okay,
Okay.
and so now we're going to start studying the intermolecular forces, and there are basically three types of intermolecular forces. Number one, being, I mean, they're called hydrogen bonds. Number two is uh, permanent dipoles, and then you have number three, which is called van der Waals forces.
Yeah.
But van der Waals forces has, I mean, it's known by other terms as well, like temporary dipole, induced dipole interaction. I mean, this the complete name for permanent dipole interaction.
Okay.
And van der Waals is also known as a temporary dipole, induced dipole
Yeah.
interaction. Okay? And there's uh, another word used, which is called London dispersion forces. As I so you have three types of forces, and remember that the first one is actually the strongest, and the last one is relatively the weakest. But also remember that the last one kind of depends on size of the molecule.
Yeah.
Okay, so the strength depends on the size of the molecule.
Yeah.
Anyways, so we have three types of forces, and we're going to start studying. Always remember that the first intermolecular force, TK, that's the strongest, and the last one is the weakest. And but the last one, this van der Waals forces, remember that if the size is really big, then the strength could act. It's not going to be the weakest. I mean, it's only the weakest if you have the same size molecules. So now let's start with the first one, which is known as permanent dipoles.
Yeah.
Amal, do you know what a dipole is?
Yeah.
What is it?
So the dipole is the like in the reaction,
Yeah,
it's like
just a rough
I mean,
idea. Give me
I know what it is. I just don't know how to explain it. It's like where like in a bond or a molecule, like one side has like a negative charge, one side has a positive charge.
exactly. So a permanent dipole is, or I'll define what a dipole is. It's uh when the shared electrons in the bond
Yeah.
are unequally distributed. I mean, that's the
Okay.
are unequally distributed, which results as a which results in the formation. Slight positive and slight negative charges on the molecule.
Okay.
So that's so I mean what you just said was correct. That's what a dipole is. Uh, why are the so now the issue is why are they unequally distributed? What's the reason why the electrons are going to get unequally distributed? Like you have an HCl molecule
Yeah.
and you have electrons that are being shared, okay, like a normal
Mhm.
bond, a sigma bond, but the electrons are lying closer to Cl. Why are they? What's the reason? Why are they closer to Cl?
Because Cl is the negative one. Because Cl is the negative one, and then the
I mean, the word that's used is that due to difference in electronegativity.
yeah.
Electronegativity.
Okay.
So Cl is more electronegative. Electronegative means
Okay.
the tendency to attract electrons and become negative. And this other one, the hydrogen, is less electronegative. Remember, we studied this earlier. What we studied was that if you look at a periodic table, the elements that are in the corner, you get elements to the right, and
Yeah.
the elements to the top, they are more electronegative. Okay? So these are the ones that tend to be more electronegative. What's the reason? Why does electronegativity increase to the right of the periodic table? What happens when you move to the right?
The atomic radius increases.
If you move to the right across the period, are the shells. I mean, we did this in ionization energies.
There's more shells.
I mean, the shells remain constant. It's actually you have more protons if you move to the right.
Yeah.
I say if you have more protons, then you're obviously going to attract more electrons, right? Shells
Yeah.
remain the same. You have the same number of shells across the period, plus the distance slightly decreases. I mean, you have the same number of shells, but the distance slightly decreases. Why?
Decreases.
I mean, and that too because of more protons. Because more protons, they attract the electrons strongly. But the main factor is that if you move to the right, you have more protons. So, for example, if you have sodium over here, sodium over here has
Yeah.
11 protons, but chlorine on the other side has 17 protons. So it's going to obviously attract more electrons, right? Chlorine, it's going to pull electrons from sodium. And what's happening when you move upwards? Smaller atoms, why do they gain more electrons? Or they have a higher tendency to gain electrons? Why is that?
Because they're more electronegative.
No, but what's the reason? Why? Oh, I mean, smaller atoms,
Because with smaller atoms, the electrons will be closer to the nucleus, so there's more attraction.
yeah, and they're going to be less shielded as well. Your
Yeah.
nucleus is going to be more exposed. Uh, like if you have iodine, you have 53 electrons. The nucleus is already surrounded by 53 electrons. So the nucleus would be too shielded. But if you have fluorine, fluorine
Yeah.
just has 9 protons. So the nucleus is more exposed. And plus, you're also right that it's a smaller atom, so they're going to be closer to the nucleus as well. So, anyways, that's electronegativity. So atoms they don't attract electrons equally. Some like to gain more electrons, some like to actually lose electrons, or they don't have that attractive power for electrons. Anyway,
Yeah.
so difference in electronegativity, and I'm going to look at there's a scale that's known as the Pauling scale. Uh, and let's look at this one. Okay, Newta. So I have no idea why this is so small. Just a second.
Okay.
Is there a way to? So this is the last attempt. No, it's still small. I said, anyways. Can I? So this what is still unreadable. 1 second. No, still. I said, anyways. We're gonna look over here at the Pauling scale. Uh,
Yeah.
Forget the numbers. It shows which elements are electronegative and like to gain electrons and which ones. So the corner is the one that's actually in red. They really, really like to gain electrons. This corner over here, they're non-metals, and the yellow ones over here, they don't like to gain electrons. They actually end up losing electrons. Okay. So is this clear? I said so. So the first thing is, uh,
Yeah.
dipoles exist. That if you have an atom and the atoms are bonded together and they're sharing electrons, the electrons would be closer to one of the atoms. Okay? So Cl would be partial negative and hydrogen is going to be partial positive. So if you have lots of HCl molecules, all those HCl molecules are going to have dipoles.
Yeah.
And if they have dipoles, That means the molecule is polar. There's a positive side, there's a negative side, positive side, and a negative side. They would start to attract, the negative would attract the positive of the other molecule. Okay, the
Yeah.
positive and negative would attract, the positive and negative sides would attract. So those attractions are going to be your permanent dipole attractions.
Yeah.
Okay. Acha, then remember that we did shapes. And when you remember that dipoles depend,
Yeah.
they depend on shape of the molecule. Okay, we did a lot of shapes, and your dipoles, they depend on shape of a molecule. They're going to get cancelled out uh, according to the
Yeah.
shape. So, for example, if I have a molecule over here, there's this carbon dioxide molecule, and it has a linear shape. Okay, it's carbon
Yeah.
has a double bond over here and a double bond on the opposite side, and there are two oxygens. Oxygens are highly electronegative, so oxygens would be pulling electrons towards themselves, right? So the double bond, I mean, the electrons over here, think of a molecule, and there's an oxygen pulling electrons towards the right, and another
Yeah.
oxygen pulling electrons to the left. Where would the electrons go in this molecule? Would it have a negative and a positive side?
Yeah.
I mean, which side would be negative?
Um, would it be like this side? The side with the oxygens would be negative,
I
with
mean,
the
this side?
carbon be positive. Yeah.
No, but the thing is, look at the shape of the molecule. It's like, I mean, think of electrons over here, and there's someone pulling electrons towards the right, and there's someone pulling electrons to the left. Where would the electrons end up? Where would the electron cloud end up? Wouldn't the two forces cancel out?
Yeah. It'd be in the middle.
Okay, so they're going to remain wherever they are because both dipoles, they're going to cancel each other out. Okay,
Yeah.
it's like two people pulling on something, and the thing would remain in the middle if they're equally pulling it. And in this case, they would be equally pulling it because both of them are oxygen atoms. Okay, so dipoles cancel out,
Okay.
and this molecule is non-polar. So then similarly, you have another. Let's think of other shapes which could be. Let's say you have an AlCl3 molecule.
Okay.
Now, in this uh, in this molecule, which atom do you think is more electronegative?
Um, I think would it be the chlorine?
Okay, so chlorine is electronegative, uh, and if chlorine is electronegative, uh,
Yeah.
so all these chlorines, sorry, so all these chlorines, they would be trying to pull electrons, right?
Yeah.
They would all be trying to pull electrons.
Yeah.
Where would the electrons end up?
And then would it be the middle again because all of them are pulling?
Exactly. So the electron cloud over here, whatever the electron cloud, it's going to remain wherever it is because one is pulling upwards, one is pulling the electron cloud towards itself, the other one is to the other side. So again, it's going to be a non-polar molecule because the dipoles would eventually
Yeah.
cancel out. Okay, so in this case, dipoles cancel out. So what about this molecule? So you have a tetrahedral shape,
Yeah.
a carbon with Cls attached to it. And again, it's a the same thing would pretty much happen in this case as well. So you've studied vectors in physics, right?
Yeah.
So it's like vectors. It's like three-dimensional vectors. I mean, you've studied two-dimensional vectors. But think of three-dimensional vectors. In three dimensions, uh, there would be vectors. One of them would be trying to pull electrons towards you. One would be trying to pull electrons uh, into the page. There would be one that would be pulling electrons upwards, and the forces of attraction are going to get cancelled out
Yeah.
again. So let's look at another molecule. This is also fan shaped. So here's your molecule, and this is exactly what the shape is going to be. It's going to be fan shaped. I mean, because there are three electron densities, right? The double bond.
Yeah.
When we were doing shapes of molecules, I had stated that double bonds need to be considered or thought of as a single entity, right? So it's going to be fan shaped,
Yeah.
and this one is also going to be fan shaped. Do you think this molecule is polar?
Yeah.
Neil, who's electronegative in this molecule?
The chlorine.
Okay, so the chlorine is pulling electrons in this direction. This chlorine is trying to pull electrons over here. What's going to happen?
Would it stay in the middle again?
Okay, exactly. The vectors are going to get cancelled out again, and the electrons are going to stay in the middle. Uh, but let's say, what about so over here? It's getting cancelling out. So the water had a bent shape because it was derived from a tetrahedral shape, except that on two sides there were lone pairs. There were no atoms attached.
Yeah.
So, and instead of H, let's add fluorine over here. Would it be polar?
Okay.
Would it be polar? Like this fluorine is trying to pull electrons to over here.
Yeah.
So are they going to get cancelled out?
No, because it's like in the similar direction.
Exactly. So the electrons are going to get pulled because they're not cancelling each other out in this case. Okay? They're not acting opposite to each other. So dipoles are
Yeah.
not going to cancel out. So you get the idea, right? Uh, let's say I'm just going to do a few more example.
Yeah.
About so here's a tetrahedral shape. Is it polar or not? Which one is going to be? Which side would be negative? Which side would be positive? About which side for this molecule?
Um, the chlorine side, wouldn't it?
Okay. And you have to when you look at bigger molecules, you have to. Uh, I mean, most of the electrons, because chlorine is very electronegative, so most of the electrons are going to be pulled towards chlorine. So all the other sides are going to be actually positive.
Okay.
Okay, because electrons are getting pulled towards one of the chlorine atoms. And I'm going to add one more thing over here. Remember that carbon and hydrogen have almost the same electronegativity.
Okay.
Almost the same electronegativity. So C and H have almost the same electronegativity. So whenever you see a carbon and hydrogen bond anywhere, okay, that
Yeah.
is likely to be non-polar. Okay, so this bond it's going to be almost non-polar. I mean, it's not exactly the same, but it's going to be almost non-polar. Okay, Amar, is this clear?
Yeah.
I said then the strength of the dipole. How do you determine the strength of the dipole? The bigger the electronegativity difference, the greater would be the dipole that's created.
Okay.
Okay, so strength of dipole, and it obviously depends on the shape as well. I mean, you can have a very large difference in electronegativity, but it's not going to matter if they're canceling out. So strength of dipole, large electronegativity difference, and that would create a bigger dipole.
Yeah.
I said it's going to create a bigger dipole, uh, and obviously it would depend
Okay.
it would depend on the shape. I said anyway, so I'm going to give you four molecules. Tell me which one has the greater dipole. For example, if I have HCl and I have HBr and I have HI, which one do you think has the greatest dipole out of the three?
Um, would it be the H and the Cl? Because
Exactly, but Cl is very electronegative, right?
yeah,
And Br is going to be it's less electronegative. I is even lesser electronegative. So that dipole created is going to become smaller and smaller. Okay. Uh, so permanent dipole becomes weaker. Acha, so not all dipoles are exactly the same. Some are very strong, some are very weak. But at the end of the day, they also depend on the shape of the molecule. Acha, so moving on, let's move to the next attractive force, which is known as a hydrogen bond. Have you ever heard of hydrogen bonds?
yeah.
Acha, do you have any idea how they're different compared to permanent dipoles?
Because hydrogen bonds can only come in like hydrogen atoms. So
Acha, are they stronger? I mean, they're significantly stronger than permanent dipoles. Acha, significantly stronger than permanent dipoles. And you can think of them as an extreme version of a permanent dipole. Like if you have a very strong permanent dipole, that basically is a hydrogen bond. So it's kind of like an extreme version, and it significantly differs. I mean, if a molecule like you had these, we did HF, we did HCl, we did HBr, and we did HI. We just did some comparisons, right? Now on the y-axis, there are boiling points. Like if HCl has permanent dipoles, HBr has permanent dipoles, and you have HI which also have permanent dipoles. But when you talk about HF, then all of a sudden HF has hydrogen bonding, and its boiling points are significantly greater than all three combined. So do you get the idea that all of a sudden when you have hydrogen bonds coming in, hydrogen bonds are way stronger compared to permanent dipoles. Okay? Is this thing clear? Amal, is this clear? Y-
I I can't hear you properly. It sounds really messed up.
Just one second.
Yeah.
Can you hear me now? No. So my point was that if a substance is forming hydrogen bonds, then it's although there's not a lot of difference between HF, HCl, HBr, HI, like
Yeah.
structurally, but HF forms hydrogen bonds, then its boiling point is significantly higher. I mean, it completely breaks the trend. So whenever a substance has a hydrogen bond, then all of a sudden its boiling point is very very high. Okay, and its physical properties are going to be vastly different because of the stronger attractive force. Okay, is this clear?
Yeah.
Acha, so when do substances form hydrogen bonds? There are two conditions for that. One is that oxygen, nitrogen, or fluorine, they should be bonded directly to hydrogen.
Okay.
Okay, that's the first thing. They should be bonded directly to. Acha, that's number one. And number two is that lone pairs. As a lone pairs on oxygen, nitrogen, or fluorine should be present. Amal, is this clear? So, Amal, we were talking about that hydrogen bonds were significantly greater. Can you hear me properly now? Nee, I think it's not working.